Let's go. Matrices are used everywhere in quantum mechanics. They let us represent quantum states and the operations we perform on them. In this video, I'll focus on how to represent quantum states as matrices and three kinds of operators: rotation, identity, and projection. Let's start with how states are written in matrix form. Suppose we have a state psi in the SZ basis, which is the base of spin along the z-axis. We can represent it as a 2x1 column vector, where C plus is the coefficient for plus C ket vector and C minus is a coefficient for minus C ket vector. The corresponding bra vector is going to be the conjugate transpose of it. Now let's look at the basis states themselves in matrix form, Z, X, Y. So plus Z ket vector in the SZ basis will look like 1, 0, which makes sense because in this Z basis it has the probability of 1 of being in its own state and the probability 0 of being negative Z. And minus Z is the opposite. For X and Y states in the SZ basis, we see 1 over root square of 2 as amplitudes, and these are the coordinates as you can see. We notice that Y basis introduces complex numbers, and this connects back to the fifth thought experiment we saw last time. Now let's move on to the operations. First, the rotation operator. It's written as r hat, angle of rotation, and the axis, which is the direction we're rotating about. For example, in this case, the operator rotates a state 90 degrees counterclockwise about the y-axis. How do we apply it? We put the ket vector on the right side of the operator. For instance, applying this operator to plus z rotates it into plus x. Rotation operators are unitary, which means that multiplying them by its adjoint gives us the identity operator. This conserves the probabilities under rotation. Here, the dagger symbol represents the adjoint of the operator. So if this rotation operator acts on kets, the adjoint is going to act on bra vectors, and together they reverse each other. Another way to think of it is if the rotation operator rotates one way, the adjoint rotates back the other way to return the state to its original position. And it is the inverse of the rotation operator. Let's look at an example of rotation about z-axis. Consider an infinitesimal rotation about the z-axis. We can represent it this way. Here, j hat is the operator that generates rotations, and it is a Hermitian operator, which means that it equals its adjoint. So let's see what happens when we apply the rotation operator to plus z spin state. And remember that the rotation is about z-axis. Obviously, the state vector should not change its direction, but it acquires a phase vector. This is because plus z is an eigenstate of j hat. Here I'm explaining how and why plus z is an eigenstate of j hat, and we deduce it through Taylor expansion. You can take a look at it. Now, before we talk about identity operators, I want to mention projection operators. So projection operators project a state onto a given axis. It's important to note that these are not numbers, they are operators. You might think that we can just take the inner product and get 1, but it doesn't work like that. That's an inner product, but we're using these as operators. So the operator projects a state onto plus z in this case and minus z here. Now on to identity operators. Basically, the whole point is that they act on a ket and do nothing. They are composed of two projection operators, and the property is that the sum of the projection operators is equal to the identity. For the z basis, it would look like this, and this is called the completeness relation, the idea that the projection operators spanning a basis add up to the identity. Each projector has eigenvalues 0 or 1. If a state lies along that direction, it will get an eigenvalue of 1, and if it's orthogonal, it gets an eigenvalue of 0. So what's the whole point of identity operators? The thing is that they're really useful when analyzing modified SG experiments. So here we had an SGX device in between two SGZ devices, and we saw that when we don't measure the spin in the middle, all particles exit the final SGZ device in the same state as they entered the first SGZ device. We can see how projection and identity operators are useful here. So when we send a spin-up particle, the output is still going to be spin up. But if we block one of the paths, for example, the spin down path. Then the projection operator explains why spin down particles get eliminated while spin up particles still come out. Now, if we want to express a state in another basis, for example, the x basis, we can insert the identity. Here I am explaining it. So this is the identity, right? In terms of x basis vectors. This lets us calculate the probabilities of outcomes when passing through an SGX device. This long equation is how we calculate the probability. Here's an important part. The first two terms sum to 1/2, and it is what we get when we make a measurement inside the modified SGX device. When we make a measurement, we are going to square the amplitudes and then add the probability. But remember that we don't measure inside the SGX device. That's why we are adding the probabilities first and then squaring them. The third and fourth terms right here, they arise because we didn't measure. They are called interference terms. With measurement, we add probabilities. The interference is destroyed, but without measurement, there is a superposition. So that was an overview of some of basic matrix mechanics. See you next week.